We'll now look at Chapter 9, which is on linear dynamical systems. It's an application area. Actually, it's used in many fields, so it's a very good thing to know about. And at its essence, it really only uses nothing but matrix vector multiplication, which is something we know about now. Okay, so let's take a look. So we'll start with what is a linear dynamical system, and then we're going to look at two practical examples. Now, the examples I'm going to show you are going to be a bit simplified, of course, but it'll give you a rough idea of how real ones actually are done. Okay, so let's start with the setting. So I have a sequence of n vectors, and we're going to call those x1, x2, x3, and so on. Now, here the index denotes something like the time or the period. Could be, maybe something about it could measure time at a fixed interval, like daily, hourly, but it doesn't have to be. It could be, for example, trading days in finance. Trading days in finance, doesn't count weekends and market holidays. So that would be, that's what that, but basically t, the subscript t here, if you have x sub t, a t is just a mnemonic supposed to hint at time. That's the idea. Okay, and these are n vectors. Notice the notation's a bit ambiguous, right? That in this case, the subscript doesn't mean the tth index of the vector x. It means x sub t, which is the tth vector in a sequence of vectors. Okay, if you want to talk about the third entry of x7, you write it like this. And the interpretation is that is the third component of x7, which is the state at time t equals 7. Okay, so that's xt is going to be called the state. X is a traditional symbol for the state, but there's lots of others that are used. And the sequence is called a state trajectory. A trajectory just tells you how something evolves across time, and so that's what this is. That's what this is called. It's a state trajectory. Now, just to give you a rough idea of how this works, if t is the current time, say it's today or something like that, then xt, we refer to that as the current state. It's the state at the time right now. X sub t minus 1, that's the previous state. So for example, if this is daily, x sub t minus 1 is the state yesterday. Xt plus 1, that's the next state. So if this were daily, xt plus 1 would be the state tomorrow. Okay? And xt, what does it represent? It can represent many things. But for example, we'll look at a couple of examples, but we'll look at one where it represents the age distribution in a population. And that means basically the entries tell you how many people there are in some population of a certain age. And xt gives you the age distribution. A very common one is in economics, where xt, the entries of xt, give you the economic output in n sectors of the economy, right? So the different entries of x tell you how different sectors did in that period. And it's very common for mechanical systems to describe this. When the entries of x are typically positions or displacements, and also they will typically include also velocities and momentum. Okay, so but the idea right now is it's just a vector sequence. Okay, now linear dynamics is this. It's a very special form. It says xt plus 1 is at xt. And that simply says that the next state is obtained from the current state by simply multiplying by a matrix. Okay? Now those matrices can vary with time. That's what this sub t is here. And a sub t, that's an n by n matrix. It's usually called the dynamics matrix or the update matrix. Dynamics is it is a very common term to refer to this, right? And we can interpret. Now there's a lot of indices flying around here, so you have to be very careful. So for example, at sub ij, so t denotes the time or the period. Another name for time or period is epoch. So I don't know, it's an old name for it, but okay. Then ij are of course the entries in the n by n matrix a sub t. And so the ij entry tells you how much the jth input to the matrix vector multiplication affects the ith output. So for example here, if you have xt, that's the state at time t or epoch t, it's the jth component, then you multiply these two together and you get the contribution to the ith component of tomorrow's, or well, that's if it's daily, but the next state component I that comes from the current state component j. Okay, so that's the interpretation. This is quite tricky. There are a lot of indices here, and you really gotta sit down and go real slow and try to understand what all these things mean. Okay, now in many cases, A does not depend on time, and so it is what people would say it's either it's constant, or you would say that it is time invariant. And then you would refer to this if it looks like this, xt plus 1 equals to simply a xt. We say that we would say that this is a linear time invariant dynamical system. Okay, so that's something you'll hear, and sometimes you'll hear the phrase LTI for linear time invariant dynamical system. Okay. Now, one thing to say right now is, of course, many dynamical systems do not evolve according to these equations, but it turns out a lot of them do either pretty well or at least approximately. And one thing to notice immediately is that you can interpret this as a recursion. And what that says, for example, is if I knew the current state, I could simply multiply by AT, get xt plus 1. I multiply that by AT plus 1, and I get xt plus 2, and so on. And so these are just iterated matrix vector multiplications. And in fact, that's called simulating the evolution of the state. If you said that, anyone would understand what you're talking about. So, and that's very cool. You could do things like say, please simulate the system forward 10 time periods, right? Or please tell me what this mechanical system is going to be doing in the next 1 second when I've sampled at a rate of, let's say, 50 times a second, right? So I would propagate forward 50 time steps to see what configuration it will be and what the state will be. So you can actually basically simulate a linear dynamical system. Now there are a lot of variations. A very common one looks like this. This is the usual update is the AT plus that's the contribution to the next state from the current state. But then people put on another term which is BTUT, and then even CT. That's less common, but does happen. Now here, UT is an M vector. U is in fact the traditional symbol, and it's supposed to be an input. So UT is an input to the dynamical system, and CT is an offset, right? So I'll give you an example, is aircraft dynamics is described by this, actually with CT equal to 0. UT is a vector that tells you about the various things you can do to control the airplane. For example, what are the angles of the control surfaces, like the rudder, ailerons, elevator, things like that, right? So that's what that is. Or one might be the engine thrust. So it would tell you things like if you were to increase your thrust, what would happen? If you were to turn your rudder, left 2 degrees, like what would happen? Okay, and that has a model like that. In fact, that's a very common model actually for all of what's called modern control. And for that matter, navigation, that there's entire courses on nothing but this linear dynamic system, right? So at Stanford, we have one. That's EE263. Okay, so B is referred to as the input matrix here, U is the input. Usually in those applications, U is something we might have control over, and so the natural questions you'd ask would be, what would be a good sequence of inputs to apply to my system? Actually, we'll be able to answer all of those questions in a few weeks in this course. So we'll be able to get a very good idea, hold on that. Okay. Another common version is something like this. This is the so-called K-Markov model. And what it says is that the next state, that's xt plus 1, is actually it's a sum of contributions from the current state, the previous state, the previous state, and so on. And this goes back k steps. And in fact, sometimes people call that the memory of the system, because basically it says that the next state depends not just on the current state. That would be a simple, basic linear dynamical system. But in fact, it depends on the current state, the previous state, and maybe, going back or something like that. So that's sometimes called the memory of such a system. And this is called K-Markov model. It's also called in other contexts, like in statistics, autoregressive or vector autoregressive, so VAR model. It's got lots of names. Okay, so that's an autoregressive model. And when capital K is 1, that's the memory. This corresponds to just a linear dynamical system. I should stop and tell you just one quick story about what state means. So there is a definition of state, and what state means is it's a summary of what you need to know about the past to be able to predict the future. That's what the state is. And if we go back here, you'll see that that's exactly what this does. So for example, if I said, please show me the next 3 states, like xt plus 1, xt plus 2, xt plus 3. All you have to know is xt. You don't have to know what xt minus 1 was, xt minus 2. It is no one's business how the system got into the state xt, because once you have xt, you multiply by at and you get xt plus 1. Then you multiply that by at plus 1 and you get xt plus 2, and so on. So the point is that xt really is a bona fide summary of the past, sufficient to allow you to predict the future, right? So some people would call it a sufficient statistic or something like that. Okay, and in a K-Markov model, the state, people would not call xt the state here. The state is actually, it's the collection, xt minus 1 down to xt minus k plus 1. Okay. So what we're going to do now is look at 2 examples in a little bit of detail. Now, obviously, they're going to be simplified, but they should give you a pretty good idea of how these things come up, how and where these come up, linear dynamical systems. And the first one is population dynamics. And we'll go over it and figure it. And by the way, once you've seen these models, there's lots of variations on them, and you'll be able to get all of it. Let's just jump right in. So here it is. What we're going to do is T is going to be years. So, and we don't mean the year 1 AD. We mean, the year relative to some fixed year, like this year or 2010, something like that. Okay, and then xt is a 100 vector. So it's 100 entries, 100 long. And what it is, it's going to represent the number of people with a certain age. And the ages are going to go 0, 1, up to 99. And for simplicity, we're simply going to assume that no one lives to be more than 99. Of course, that's not the case. When people build real models like this, they actually go up to like 115, just to kind of cover essentially at that point everyone. Okay, but just for fun, 100's a clean number. We just assume everyone is between 0 and 99 years old. Okay, so xt 1 is the number of 0-year-olds, people who are not yet 1. And xt, let's say 12, is the number of 11-year-olds. Okay, so that's how that's going to work. And that's in time period t, or sorry, year t. Okay, so for example, if you wanted to get the total population, that's 1 transpose xt. So that's the vector of all ones. So you know that if you take the inner product of the ones vector and a vector, you sum all the entries. And so this is adding up everyone who is alive, right? So it's everyone who has an age between 0 and 99. In our model, there's no one alive older than 99. Okay, but if you wanted other things, it's like, for example, this vector, I should say what that is. That is concatenation of 2 vectors, or stacking. And first we stack 70 zeros on top of then 30 ones. And what that's going to give you is the total. It's going to sum x71, x72, x73, all the way up to x100. And that's all the people who are age 70 or older. Okay, so for example, if we were to simulate xt out several years and then ask, how many people will be will be 70 or older in 5 years from now? These are the ways we would do it. Or how many people would be high school age, for example? You could construct another vector here that would pick out the people of a certain age range, and it would give you that. Okay, so this is the idea. So now you know what the state is, and you know what t is. It's years. Okay. So this is from the 2010 census in the U.S., and it shows the age distribution of people of different ages. And I mean, I don't know, you can look at, there's people who study this and who know a lot about demographics and things like that. But nevertheless, it's kind of interesting. You can see that there's kind of a constant number of people up to about age, I don't know, up to, well, let's go out to here, give them the benefit of the doubt, maybe late 50s, right? Then, sorry, this is, yeah. Oh, by the way, some of this is going to get kind of morbid. Okay, so then you can see that this thing drops off, and well, that's because people are dying. Okay, so so let's see. For example, by the time, let's see, by the time you hit 70, you know, roughly speaking, sadly, I guess about you get about half the number of people who are between roughly 0 and 50, right? So that's the age distribution in the U.S., right? By the way, people who study demography would know what this is. They'd say, "Oh, yes, that's the baby boom." I mean, I don't know actually, honestly, but I mean, they could actually point to various things and say, "Yeah, that we know what that is," and all that kind of stuff. Okay, so this is the picture. Oh, and this is xt. So this is actually specifically if t equals 1 means 2010, this would be x1. This is the vector. We're just plotting it. Right? Okay. Now, the way the number of people in the U.S. propagate from year to year. And I should say that we're going to ignore immigration and emigration. Right? So we're going to ignore that entirely, although one could easily include that. That would be an additional term, like the UT that we talked about earlier. But we're not going to now, just to keep it simple. So how does it propagate? And we have to ask ourselves the question, what is the population distribution next year, given the population distribution this year? And so, let's figure it out. I mean, basically, it's going to go like this. So how many 0-year-olds will there be next year? Well, the answer is, basically, those are the people who were born that year, because anybody who was already counted last year is going to be at least one on the next is going to be at least one on the next time. Okay, in the next time step. So basically, the next year, the first xt plus 1 sub 1 is the number of people who were born that year. Now, how many people are age 27 next year? That's got a pretty simple answer. It's the people who are 26 this year, sadly, minus those who died that year. So. And yes, 26-year-olds do die. It's very sad. The good news is it's pretty rare, but nevertheless, some do. And so the number of 27-year-olds next year would be equal to the number 26 this year. And then maybe you'd have to subtract off the people who died, the small number of people. Okay, so that's explained. That's going to be by that we're going to explain by the so-called the death rate. And DI, that's going to be the portion of those who are age I minus 1. Who end up dying this year, and therefore don't make it, don't count in the next year. They're not around, right? And we'll take D100 equals 1. That kind of means, at least in our simple model, once you get to be 99, you'll die. Period. Okay. Okay. Now the other one is the birth rate, and the birth rate is a vector in R100, and what it says, it's going to tell us, the birth rate is going to tell us how many people are born to people of that age. Okay, so, and there's some pretty obvious things you would know about that, and we'll look at both of these things. We will end shortly. I should say that in fancy population dynamics models, both the birth rate and the death rate also change with time for various reasons. Social reasons, but health technology advances and things like that. But we're going to just assume they're constant. Okay, so these are birth and death rates in the U.S. I think the birth rate, I think, is given in 5-year chunks, but whatever. Here it is. And you can see a lot of things. Yes, so guess what? Not surprisingly, there are no children born to 0 to 10-year-olds. Oh, I should say 1 to 10-year-olds. And there's also basically 0 born to people. I mean, at least visually on the plot, doesn't look like that. People age 50 or 60 don't, and older are not having kids. Okay, and you can see the big bump here, and I guess it peaks in the U.S. between 25 and 30, right? So that's what this is right here, and it says that it's about, I don't know, a little shy of 5%. So that means if you are, I don't know, 27 and you're in the U.S., then just under 5% of you will have a kid that year. By the way, that's not going to include the men, obviously. So if it's about 50-50, that's somewhere around 9%, right, of women will have a baby in the U.S. at age 27. Okay, now let's look at the death rate. That is this vector D, and we're writing it in percentage. And what it says it says that, I mean, it's not surprising. It says the death rate is very low until you get to be, I don't know, 55. And then you can see it starts going up and up and up. So I'm about right here, by the way, just in case anyone's curious. So I'm right at the beginning of the hill, okay, which is, I guess, not cool for me or something. Anyway, so what happens then is, by the time you get to 80 or 90, yeah, for 90, it's about 10%, right? So maybe even more. That's like 87. But anyway, for 90, yeah, it's probably something like 12% of 90-year-olds are going to die in the next year. So that's the idea. So this plot looks kind of like what you'd expect it to look. It kind of makes sense. And over here, you see a little tiny thing there? That's real. And what it is that some people refer to a death rate that goes down, is flat, and then goes up again as the bathtub or something like that. I mean, here it's not very pronounced, right? But it basically says that there are a lot of infants, very young people who die between 0 and 2 or something like that. Certainly 50 years ago, this was much more pronounced, right? Or 100 years ago, it was definitely more pronounced. A lot of kids just didn't make it, like in the 19th century, for example. So, okay. But the point is, these pass the test of being reasonable. I mean, they're correct. They're from the U.S. Census, so there they are. Okay. Now we're going to construct the dynamics, and that means we're going to construct this 100 by 100 matrix that maps the current U.S. population density into next year's population density. And the way we're going to do that, it's pretty simple, is the number of 0-year-olds next year is the total births this year. Now that's equal to that's the inner product. I take the birth rate vector, that's B, it's a 100 vector, and I take the inner product of that with xt, right? Because B, let me give it a real one. B25 is actually the number, it's the number of kids that a 25-year-old is going to have. Now it's small, it's 0.03 or something like that. But then I multiply by the number of 23-year-olds or 25-year-olds, whatever I chose, right? And then we get the whole thing. And you add all that up and you get this, okay? No, not surprisingly, B is 0, between like 0 and 10, and certainly above 70 or something. So it says that 0 to 10-year-olds and people above 70 are not pulling their weight in terms of having kids, right? But that's, I guess, well, that's biology. So, okay, all right. So, and that gives you xt plus 1 sub 1, because xt plus 1 means next year's population distribution. Sub 1 means the number of 0-year-olds. Okay, so, and it's simply equal to B transpose X. Okay, now the number of I-year-olds next year is going to be the number of I-1-year-olds this year minus those who die, right? And if the death rate is DI, it says that xt plus 1, I plus 1, and you really have to read these very carefully because otherwise, it's very confusing. This says the population distribution at next year sub I plus 1. That's the number of I-year-olds next year. And that's equal to the current number of I-1-year-olds. That would be this thing, minus the fraction who die. and that's going to be minus di. So it looks like this. And this is true for I equals 1 up to 99. And so if we assemble all of this into a matrix, we get this matrix here, which is A is this thing. The top row tells you about the birth is literally the birth rate. Then the next rows are very interesting. Each row only has one non-zero entry. So for example, and by the way, that makes sense. Let's actually interpret what that means. And you can check. You can put an xt here, right? And this becomes xt plus 1. And you can just kind of work out see that it makes sense. But let me just say a couple things about this matrix A. By the way, it has a name. I mean, you don't need to know it, but it's called a companion matrix. A matrix that's got a row that's non-zero and then kind of a subdiagonal that's non-zero. Doesn't matter. Oh, it's a super sparse matrix. I hope you noticed that because it's a 100 by 100 matrix. So there's 10,000 entries in that, in total entries in that matrix, and yet only 199 of them are non-zero. So, when a matrix has only 199 non-zeros out of 10,000, it's sparse. So that's a sparse matrix. Also, let's interpret a couple things. Like each row here mysteriously only has one non-zero. Well, what does that mean? Well, what it means is this. A row tells you how do you get next year's number of people of a certain age, right? And what this says is there's only one way to make a 28-year-old. The only way to make a 28-year-old is got to be someone who was 27 last year, like period. That's it. So that also kind of makes sense. You can look at columns, right? So columns are interesting. If I look at a column here, it's super duper interesting. If I look at, let's say, the 29th column, that corresponds to people who are 28. And the top entry tells me how many kids did they have, right? And then if I go down here, I'll find another entry, which basically is a number slightly less than 1, which tells us basically those 28-year-olds are going to be 29 next year, except for the small fraction who die. Okay, so that's the picture. So there's your matrix. It's xt plus 1 is A x of t, and we're going to assume it's time invariant. If you do real demographic studies, you actually predict that these things are changing over time. I should also add, in real demographic studies, you would do this for subpopulations and kind of estimate them differently or something like that. But the point is, this is a basic population dynamics model, and it's a linear dynamical system. Okay, so here's what we do. So we can actually now do a simulation. Now, this is the simulation, and let me explain how I got it. We started with this. That's the population distribution of the U.S. in the 2010 census, right? So that we'll just assume that that's correct, right? Okay, so we take that and we then multiply it by this matrix A, which is our dynamics matrix. That gives us the 2011 distribution. By the way, not the exact distribution, but sort of our model's prediction of it. Then I multiply by A again, and I multiply by A 10 times, and I get this. Okay, so that is our prediction of the 2020 distribution, and that's ignoring immigration and emigration. Okay, so so that's interesting. By the way, the current year is 2020, and the census is being carried out right now. So we could have a drum roll when the census is done and compare this plot to what the U.S. Says it really is. Honestly, it's probably going to be pretty close when we ignore immigration and things like that. It won't be exactly right, but it'll be pretty close. And you see interesting stuff here. That's it. You can look at it and make, demographers would make a big deal about, like, what is this thing? And I don't know, what's that? Or what, I don't know. So they would say, but they would have lots of interesting things to say about it. So this is the kind of idea. Now, I'll just mention a few things about how, it's completely clear that this is useful. Extremely clear, right? Because, for example, if you were a school district, you might ask, how many kids are going to be in high school 10 years from now? Because if it's going to be a lot more than currently, we may have to float a bond, build another school, something like that. So that's the kind of thing you might do. Or you might ask yourself, how many people will be retired in the next 15 years, right? Because that would be that could tell you. I mean, so there's all sorts of stuff you could do with models like this. But this is the basic idea. Okay, our next topic is epidemic dynamics. That is, well, it's quite topical because I'm sitting here all alone recording lectures, which is frankly ridiculous, but I'm doing it precisely because we have a pandemic raging, especially in the United States, I should add. So here I am doing. So this is actually quite topical. I should say that this example was in the book and in the course, for the last couple of years. So this was not prescient or anything. But what I'll do is show you how it's another example of how linear dynamical systems are used to model certain things. Once again, this is what I'm going to show you is a highly simplified epidemic dynamic model, but nevertheless, it's one that kind of gets some cool. I mean, it kind of gives you it would be a good start. So let's take a look at that. We'll look at something super simple. It's called the SIR model, and what it does is your state is a vector. It's got 4 entries, and that's it. And they are. It's the proportion of a population which is susceptible, like that. So that means if you're susceptible, it means that you don't have immunity, and well, you're not dead. Okay, so in which case you're not susceptible. You could be infected, right? That's another fraction, and that means you actively have the disease on that time period. You actually have the disease. Recovered means you had the disease and you're now immune. Okay, so that's kind of, again, the idea. And then finally, we have deceased. That's the number of people who had the disease and unfortunately died. Okay, so we have, and this is called SIR model. There's many other models, much more sophisticated and so on. So for example, if I told you that XT was that number, we would say, well, in that population, 75% of the population is susceptible, meaning they could catch the disease. 10% actually actively have the disease at time period T. Another 10% had the disease and they've recovered and they're now immune. And very sadly, 5%, that's the 0.05 here, actually had the disease and are dead. They died. So this is what this vector means. Okay, so so epidemic dynamics. So here's the model, a very elementary model. It goes like this. It says we're going to do daily. So on every day, it says the following: for every among the susceptible population, 5% actually acquire the disease, right, and 95% don't. They just remain susceptible, right? So by the way, these are the kind of interesting things you could do. If people, like, for example, wore masks or something like that, or practice social distancing, you could push the 5% down to maybe 2% or 1% if you're lucky, right? That's the kind of thing. Okay, but we'll just say it's 5%. Now, among the infected population, here's what happens on each day. Very sadly, 1% of them dies. So among all the people who are infected on a given day, about 1% of them die. Now, 10%, however, recover. So that means on the next day you're recovered and you have immunity. Now we can also have this: 4% recover. That's good, but they recover without immunity, right? And so that's just, and I'm just making this up. It's just an example I'm making up, and that means that they're back to being susceptible. And 85% just remain. If you're infected today, you'll be infected tomorrow, right? And you will not transition to any of these other statuses. And let's see, if you are immune today, you're immune. You're going to be immune tomorrow. By the way, we could change this to 0.99, and now 99%. That'd be very interesting, and you could transition from immune to susceptible, and that would mean that every day 1% of people who are immune actually become susceptible again. Okay, so I'm just saying we could do that. We're not going to. We're just going to say once you have immunity, it's forever. Okay. Oh, and of course, if you're dead today, you will be dead tomorrow. That's part of the model. That's actually a pretty realistic assumption, I think. Okay. So now when you assemble this together, you basically have to say, what is the next state as a function of this state? And you have to write it as a matrix A. That doesn't have to be called A. Can be called anything you like. And you're going to multiply it by the current state. Okay? And so here's what you get. So we got this matrix here. It's 4 by 4. It's 16 numbers. There's a bunch of zeros in it. But let's audit some of it and make sure we understand it. So let's see. What is this number? Well, that number tells you, it says that this multiplies the first entry. This is today's state. And the first entry of that is going to be the people who are susceptible. And it says that it contributes to who is susceptible on the next day. And this says that you multiply by 0.95 the number of people susceptible today, and that'll be the number of people susceptible the next time, or the contribution from them. There's also this one, which is super cool. The second one are the people who have immunity. And this says that, who have the disease, who are infected. And 4% of them go back to being susceptible. And that's what this component is. Let's just check another one. Let's see, what does that one mean? That's 0. Let's audit it and make sure we know. By the way, what we're doing here is super important. Don't ever just write stuff down and say, oh, cool. Yeah, I mean, look at the numbers, audit, take a random entry and see and make absolutely certain you can understand it. So let's look at this one. That says, who is going to be, this says, what is the number of deceased people as a function of the current state, susceptible. Now, in our model, we don't have people going from susceptible to dead. Actually, you could easily. That could be, some very small number, and that's people who died not from the disease. So this doesn't have to be 0. It is 0 in our model, but it could be some very small number that tells you about people dying by other non-disease related deaths, right? Let's see. Here we go. What's this one? This one says that you look at the number of people today, or the fraction of people today who are infected, and then it says you multiply that 0.01, and that's the number of people who die over the next day, right? So this is it. Okay, so I'll leave that here. And anyway, so it's very important, and you should probably take some time to actually audit essentially all the entries in there to make sure you understand them. But the point is, now we have a beautiful linear dynamical system. I can start, for example, with everybody susceptible, and then just propagate it forward, and we'll just see. We can make predictions about how long is it going to last, what's going to be the ultimate effect, all sorts of stuff like that. So here we go. We are going to start with a purely 100% susceptible group of people. No one has immunity. That's it. So everyone is susceptible. And I'm simply going to multiply. I mean, it's very simple, the simulation. I just run a loop. I multiply that vector by this matrix, and I get the fraction after one step, right? By the way, that fraction will be the first column, because the x1 is, if x1 is e1, that's what this says here, it's e1, then you multiply by a and you get the first column. So after one step, we know what it is. Then I multiply by a again and again and again. And let's just take a look at what happens. Well, it's kind of cool. So here's what happens. There's a whole, everyone is susceptible. Very quickly, the infections ramp up. Now, what's kind of cool is the infections top out at about 20% of the population, right? And then they start going down. And you might ask why, and you'd say, well, probably for a couple of reasons. One is depressing. One is that some people just died and they're no longer susceptible and they're not going to get the disease. But the other thing is that among all the people who are infected, a bunch become recovered and acquire immunity. And that's this green curve. So this is when you hear people talking about herd immunity, I guess they're talking about, some effect like over here or something. That's kind of the idea.